the structure, if you remember the structural causal model, for this causal graph, the structural causal model will look like this. The COVID symptom that takes the some exogenous noise and some hospital location that we can observe, we represent UCN, and it generates its value. Then FX is the like chest X-ray image. It takes the COVID symptom value and some noise, and then generates that images. Finally, there's like pneumonia diagnosis that takes the chest X-ray image and the hospital location also, and then it generates its value. Now, these are like unknown structural functions for high dimensional variables, right? How can you actually know that? So we have the deep causal generative model that is like similar to causal GAN, if you remember. We can use one neural network for each of these variables. So what will happen for COVID-19 symptom and pneumonia diagnosis, both are like low dimensional variables. So what we do is like maybe we use single multi-layer perceptron MLP that takes this Gaussian noise, and as I mentioned earlier, that when we have unobserved confounder, we have some Gaussian noise for that also. So we feed both source of noise to this mechanism, and we generate C. So this GC, this generator or GAN will represent this XC. Next, since X is a high dimensional variable like X-ray image, we use a convolutional neural network that takes this COVID value and also some noise to generate the corresponding X-ray image. And finally, we have this, and this GX will try to mimic f of x. And finally, we have like GX that is GM, that is like how the pneumonia prediction will be done from this X-ray image, and also this like some confounding noise. So if you remember, I said like for when we have another confounder, we sample one vector and we feed it to both mechanism. So here we sample same Gaussian vector and we feed to both this like COVID vector mechanism and also pneumonia diagnosis mechanism. That is how we feed this observational distribution. So after that, we can generate fake data from here, and we have real data. Then we can match this observational distribution, and then we can train these neural networks, right? But there's a problem. That is, here if you see C, COVID symptom and pneumonia diagnosis, these are like low dimensional variable. But X-ray image, that's a high dimensional variable. Let's say X-ray, like that's an image, right? So when you try to use GAN to match this observational distribution, maybe you just directly concat this C and N with an image, and then try to like use a discriminator. Then the discriminator actually cannot learn properly. It just ignores the low dimensional variables. It just focuses on the X-ray image. So even if we need to learn this joint distribution, it just trains this, gives the it just matches this image, and based on that loss function, it tries to maybe train this model. But this model does not get trained that much, because when there's like imbalance between their dimension, and low dimensional variables are just getting ignored. So what we do is like, so how to deal with this situation, right? So like there's a paper, modular learning of deep causal generative models for high dimensional causal inference. They do is they try to modularize the training process. So okay, since we cannot learn the whole joint distribution, we'll try to modularize the learning process. So here they propose a modular training based on C component factorization. That is, here C component is a group of variables that are connected by unobserved confounders. For example, here hospital location causes both this COVID-19 and pneumonia, so that's a C component. Just say that's is not connected to another variable with unobserved confounder, so that's another C component. So they do is like they split this training process based on C component. So now, okay, what does that mean? So they will do is like train models, all of them, but first they will train this convolutional neural network, and then they will train this GC and GN. So first they will train this convolutional neural network that matches this f of x, and then they freeze it, and then they train this like remaining two neural networks. Since we are not training all of them together, now it actually gives us better convergence, and also like theoretically guarantee that the all joint distribution will match. Okay, so till now I discussed the like interventional I discussed algorithms that can handle interventional query. Yeah, but what are the open problems, right? So one open problems, I'll like shortly go through them. That's like positivity violation. That means, okay, if you don't have maybe suppose propensity score, that's like really imbalanced. or you don't know what will be some outcome given your treatment and covariate, or you don't know, okay, like maybe you don't have enough data, like some person didn't take any treatment. So these are positive evaluation, and then your like prediction will be biased. So all these algorithms like assume that we don't have positive evaluation. So that's an open problem for us to deal with. Then one major thing is like we are always assuming this we have a DAG or the directly acyclic graph. If we have acyclicity violation, then we don't know what to do. So that's another open problem. And finally, there's one thing like I always hear from reviewers that is, okay, you are assuming you have access to the color graph, and like, okay, well, that's a major assumption. But like, I don't know, maybe we need more algorithms that can do causal discovery. Yeah. So that's also an assumption we need to address, and open problem that we need to deal with. Okay, so now let's correlation with table data, but for counterfactuals. What does it mean? So we know that like there's 3 steps of counterfactuals. One is in parse hierarchy. That is like, suppose given a model M, that is structural causal model, and P of U, that the distribution of the exogenous noise, and we want to estimate this quantity. That is the B is the suppose outcome, X is the intervention, and E is some evidence. So this is the counterfactual question, and the in sentence is like, if it were X, then B. So like, what is the probability of like happening B if I intervene on X given some evidence E? So what are the this is the query we want to answer, or we want to evaluate. The actual like steps are abduction, action, and prediction. So we have some evidence. We want to get posterior of the exogenous noise based on that evidence, and then action is like, okay, we have the posterior of the exogenous noise. Now I change the value to do X to some the intervention value, and then like that's the action, like we're changing the value. And finally prediction is like, we have the posterior of the noise, we have the intervening variable, now do ancestral sampling, right? So one example maybe I'll give is like, suppose I want to understand for a specific patient